Hey everyone, and welcome. Today we're going to totally break down one of the most important chapters in chemistry, solutions. And you know what? Our goal is simple. I want to give you a crystal clear roadmap so you can nail every single key concept and just crush any question that comes your way. So let's be honest. Have you ever felt just a little bit lost in this chapter? Yeah, you're not alone. I mean, with all the different laws, the formulas, the concentration terms, it is super easy to get turned around. But hey, don't worry, we're about to make it all make sense. I want you to think of this as your personal guide. We're going to walk through this whole chapter, piece by piece, and I'll show you exactly how each concept clicks into the next one. Seriously, by the end of this, you're going to see the big picture and feel totally confident no matter what they throw at you on an exam. So, here's our game plan. First, we're going to learn the language of solutions, how to talk about concentration. Then, we'll dive into the rules of solubility, which is all about why things mix. After that, we're hitting the big one, colligative properties. And we'll wrap it all up with a real pro-level concept, the Van 't Hoff factor. So, let's jump right in.
First things first, we gotta learn to speak the language. And in the world of solutions, that language is concentration. We're gonna kick things off by clearing up two terms that sound almost identical but are actually totally different: molarity and molality.
Okay, let's start with molarity, with a big capital M. It's actually pretty straightforward. It's just the moles of the stuff you're dissolving, that's the solute, divided by the volume of the entire solution in liters. The key takeaway here? It's all about the total volume of the final mix.
And now, let's talk about molality with a lowercase m. Now, it looks similar, right? But here is the crucial difference. It's the moles of solute divided by the mass of the solvent only, and it's in kilograms. See? It doesn't care about the final volume at all, just the mass of the liquid you dissolved your stuff in.
So why on earth do we need both of these? Well, it all comes down to one thing: temperature. Think about it for a second. When things get hotter or colder, what happens to their volume? It expands or contracts, right? So, since molarity depends on volume, it is temperature dependent. But mass doesn't change with temperature. That makes molality temperature independent, which is way more reliable for a lot of high-precision lab work.
Okay, so now that we know how to describe solutions, let's get into our next big topic, the rules of solubility. These are the principles that tell us why things dissolve, and just as importantly, how much can dissolve. Let's kick things off with gases dissolving in liquids. This is all about Henry's law. And honestly, it's pretty intuitive. The more pressure you put on a gas that's sitting on top of a liquid, the more of that gas is going to dissolve into it. It's like you're literally just shoving the gas molecules into the liquid. Simple as that. And you know what? We see Henry's law in action all the time. That fizz in your can of soda, that's just carbon dioxide gas dissolved under super high pressure. It's also why scuba divers have to be careful about the bends. That's nitrogen bubbling out of their blood if they come up too fast. And for mountain climbers, the low air pressure at high altitudes means less oxygen dissolves in their blood, which can lead to a really dangerous condition called anoxia. All right, so what about when we mix two liquids that both evaporate easily? You know, the ones we call volatile liquids. For that, we turn to Raoult's law. This helps us predict the total vapor pressure above the solution. Put simply, how much each liquid contributes to that total pressure just depends on its mole fraction, which is basically its percentage of the total molecules in the mix.
Now, when a solution follows Raoult's law perfectly, we call it an ideal solution. And this graph right here shows you exactly what that looks like. You can see it, right? As the mole fraction of one part goes up, its vapor pressure goes up in a perfectly straight line. The total pressure is just the two lines added together. Super clean.
But of course, the real world is messy. Most solutions are not ideal. They're non-ideal, which means they deviate from Raoult's law. See, in a perfect mix, the molecules don't really care who they're next to. But in non-ideal solutions, the different molecules are either more attracted to each other or, well, less attracted to each other than to their own kind. And that messes with things, causing changes in heat and volume when you mix.
And hey, here is an absolutely fantastic exam hack to help you spot these deviations in a snap. If you see an example with alcohol in it, it's almost always going to show positive deviation. And if you see an acid, it's a pretty safe bet it shows negative deviation. That is a killer little trick to keep in your back pocket for test day.
All right, let's power on to our third major topic, colligative properties. Now this is where things get really interesting, because these properties don't care about what the solute particles are, they only care about how many of them there are.
It's all about quantity over quality here.
There are 4 big ones you've got to know. When you dissolve something, you lower the vapor pressure, you raise the boiling point, you lower the freezing point, and you create something called osmotic pressure. Now, the really cool part is that by measuring these changes, we can actually figure out the molar mass of the thing we dissolved. Let me show you how.
So first up, vapor pressure lowering. When you add a solute that doesn't really evaporate, its particles kind of just get in the way at the surface. They make it harder for the solvent molecules to escape into the air. So the vapor pressure drops. And if we measure exactly how much it drops, we can work backward to find the molar mass of that mystery solute. Pretty cool, huh?
Next up, boiling point elevation. And this makes perfect sense if you think about the last point. Remember, a liquid boils when its vapor pressure equals the pressure of the atmosphere. Well, we just lowered the vapor pressure by adding a solute, right? So now we have to pump in more energy, more heat, to get that pressure back up to boiling. The boiling point goes up. And again, we can use that change to calculate the solute's molar mass.
The exact same logic works in reverse for the freezing point. Those solute particles get in the way again, but this time they're disrupting the nice, orderly crystal structure the solvent is trying to form when it freezes. That means we have to get the temperature even lower to force it to become a solid. This is exactly why we put salt on icy roads in the winter. And just like before, measuring this freezing point depression is a classic lab technique for finding a solute's molar mass.
And finally, we have osmotic pressure. This has to do with osmosis, that natural tendency for a solvent to move from a less concentrated area to a more concentrated one. Well, osmotic pressure is just the amount of external pressure you need to apply to stop that from happening. This method is especially awesome for finding the molar mass of huge molecules like proteins and polymers.
We are so close to the top of the pyramid, you guys. Okay, so all those calculations we just talked about, they work perfectly for solutes that stay as one single molecule. But what happens when stuff breaks apart in a solution, or even clumps together? Well, we need a way to fix our math.
And that fix is the Van Hoff factor, which we represent with the letter I. Think of it as a correction factor. It adjusts our calculations for the actual number of particles floating around. So, for example, when you dissolve table salt, it splits into 2 ions, right? So its I value is 2. We just multiply our colligative property formulas by I, and boom, we get the right answer for stuff that breaks apart.
And there you have it. We've literally built a complete pyramid for understanding this entire chapter. We started at the base with the language of concentration, we moved up to the rules of solubility, then we mastered the 4 colligative properties, and we put the final piece on top, the Van Hoff factor, to make all our calculations perfect.
Seriously, think about it. You've gone from maybe feeling a little lost to having a solid roadmap. You've got the structure, you've got the key concepts, you've even got a few tricks up your sleeve. What might have seemed super complicated before should feel way more manageable now. You are absolutely ready to ace that exam. You've got this.